Let's begin again. We have learned that spacetime are not the same everywhere, it varies from point to point. This difference in spacetime from place to place means that spacetime itself is curved. And this coordinate system here is the one that represents that curved spacetime. The coordinate system of absolute time and absolute space is represented like this, in the form of a rectangular coordinate system. Now, a universe without matter or energy, although such a universe does not really exist, would be shown using this kind of coordinate system. But the real universe, the one with matter and energy, looks like this. However, we cannot directly see such a coordinate system. This is because the masses of the Sun and the Earth do not have enough influence to bend spacetime very much. The curvature they produce is extremely small. So we only perceive spacetime in a form like this. To actually see such a strongly curved coordinate system, we would have to go near a black hole. Then spacetime would appear distorted in this way. So, how do we define an axis? Think of a laser pointer. If you shine a laser pointer straight ahead, the beam travels in a straight line. You can think of an axis in the same way. In flat spacetime, where there is no matter or energy to curve it. If you shine a laser pointer, it goes straight. And the path of the light becomes the axis. But in curved spacetime, if you shine a laser pointer from the origin, the beam bends because space itself is curved. That bent path defines the coordinate system. The reason we normally don't feel this curvature is because the mass of the Earth or the Sun is not large enough. So the curvature they cause in space is extremely small. And to us spacetime still looks flat. But near a black hole, if we could observe the coordinate system, it would look like this. This is the true form of curved spacetime. Now, imagine this. In an empty universe with nothing at all, spacetime looks like this coordinate grid. But if a massive black hole passes through, the coordinate system itself becomes bent and distorted like this. The grid itself bends and twists after the black hole passes. The grid slowly returns to its original form. If we were to live permanently near a black hole, we would always experience spacetime in this distorted way. Now, we humans live on the surface of the Earth. The spacetime around the Earth are also curved, though only slightly. The Earth's mass curves spacetime. But the effect is so small that when drawn to scale, the distortion looks like this. Just a tiny bend. We are standing on the Earth, which is itself moving through outer space at a constant velocity, because we live within the spacetime curved by the Earth. This is the coordinate system we always inhabit. But since Earth's mass is relatively small, the curvature of spacetime it produces is barely noticeable. So to us it still appears almost flat. However, in reality we exist within this subtly curved spacetime. As I explained earlier, each axis is independent, orthogonal to the others, and not influenced by them. You, and you are all mutually independent. None affects the others. In a curved coordinate system, the x-axis is denoted u, the y-axis u, the z-axis u, and the time axis is denoted u. In flat rectangular coordinates, we use unit vectors. You already know them well, the I, j, and k unit vectors. With these, we can represent any point in space. For example, suppose we want to describe point A. Let's say A is a vector. To represent vector A, we express it as a combination of the I, j, and k unit vectors. Each scaled by its own magnitude. For instance, if the coefficients are, and the position is written as I plus j plus k. In this way, any location can be represented with unit vectors. As we have already learned in basic vector mathematics. In the same way, in curved spacetime, the concept of basis vectors also exists. But here, as you can see, there are actually more of them. To explain them all would take time. So let's focus on the I vector. The I vector points in the same direction as the x-axis. A unit vector is simply a vector of magnitude 1. So the I unit vector has length 1 and is parallel to the x-axis. That much we already knew. But there is one more aspect we must consider. Take the YZ plane, for example. The I unit vector is also perpendicular to this plane. In flat rectangular coordinates, the I vector is tangent to the x-axis. And at the same time it is a normal, perpendicular, vector to the YZ plane. The same is true for the J and K vectors as well. They have this dual, but in a curved coordinate system, the situation becomes more complex. In curved spacetime, let's look at this vector G. The G with a subscript below can be thought of as a unit vector in curved space. It is called a basis vector. For example, G with a subscript is the tangent vector along the u-axis. Meanwhile, when the subscript is placed above, as we saw earlier, if you take the surface defined by u2 and u3, that surface is curved, perpendicular to that surface. At a given point, the vector is. In other words, it is that is when we use the subscript above. So the vectors with subscripts below are called covariant basis vectors. And the ones with subscripts above, which are perpendicular to the surface, are called contravariant basis vectors. This is where things become a little different. Because we are so used to the rectangular coordinate system, we tend to think but in fact that is not the case. In curved spacetime, each basis vector splits into two types. The same goes for u and u. Even time, since we live in 4 dimensions, is also split in this way. It's hard for us to visualize, but mathematically it is treated as divided. That is how it works. So in a rectangular coordinate system, when we represent a vector A, there is only one way to write it. That's because the covariant and contravariant bases coincide. They are the same, so there's no distinction. But in curved spacetime, since the basis vectors split into two types, the very same vector can be expressed in two different ways. That's why it appears twice. For an arbitrary vector A, another key idea in curved spacetime is that the concept of a vector itself doesn't quite exist in the same sense as in flat space. Vectors are really defined only in the flat rectangular coordinate system. Vectors in a curved world, where the axes themselves bend, the idea of a single vector breaks down. To address this, we introduce another concept. But the idea of a single vector breaks at a given point for an instant. You can imagine the space as if it were flat. So when we talk about such an instant, we say at that moment, we can represent unit vectors. By taking this instantaneous viewpoint, vectors can be defined. So the concept of that moment. This is called the momentary co-moving reference frame, abbreviated as MCRF. At a particular point, at a particular moment, an event. At a particular moment, we describe the system at that exact event. It is explained using the simpler term local coordinate system. Momentary co-moving reference frame. So what the book calls a local coordinate system corresponds to the MCRF. In such a local system, at a given point, at a given moment, a vector can be represented using the basis vectors defined at that instant. We can represent a vector A at that point in time. One way is to use the covariant basis defined at that moment. Vectors are written this way. Another way, at the same instant, with the superscripts, using the contravariant basis. So the same vector can be expressed in two equivalent ways, one with the covariant basis and another with the contravariant basis. When using the covariant basis, the numbers in front, say, and are called coefficients. The basis vector indicates direction, while the coefficient gives the magnitude. These magnitudes are written with superscripts. A superscript 1, a superscript 2, a superscript 3. Conversely, when using contravariant basis vectors, the indices are written as subscripts. So, in this book, because we are dealing with curved spacetime, because we are dealing with curved spacetime. From this point on, everything will be expressed this way. And then, what is important is, when expressing in this book like this, to write all of it one by one is an enormously great task, because the basis vectors become two. It becomes so physicists use a shorthand called index contraction. Just combine it all into I. And then combine this into subscript above I. Just subscript above I like this. This compact form saves us from endless repetition. Vectors are written this way. So, in curved spacetime, the covariant basis vectors are called covariant, and the ones with superscripts are called contravariant. This is the first time, in general relativity, that we enter into such precise mathematical notation. Up until now we mostly discussed concepts, but from here on we express them mathematically. That's why covariant and contravariant appear in curved spacetime. When describing curved spacetime, because the basis vectors split into two kinds, we must clearly distinguish them. This distinction is essential. Only then, can physical phenomena be represented correctly. If we ignore this distinction, the description is wrong. All the calculations would yield incorrect results. Because we live in a universe where spacetime is curved, we must treat the basis as two distinct sets, and use them accordingly. Until now, however, in engineering and applied sciences, we have not had to make this distinction. Since Earth's mass is relatively small, the curvature of spacetime it produces is extremely slight. So for most purposes we can approximate it as flat. That is why engineering calculations have worked fine. Using ordinary rectangular coordinates, without considering curvature. But in the theory of general relativity, the basis vectors must be separated into two kinds, covariant and contravariant, and used appropriately. Only then, if we imagine traveling near a black hole by rocket, can we accurately predict what changes we would observe. So, when we use both covariant and contravariant basis, only then is the description. Only then, if we go to travel by rocket near a black hole, the changes we experience could be predicted with accuracy.